Hello and welcome. Today, we will be discussing time. What exactly is time? It is more than just clocks and calendars. Think of it like a river, always flowing forward. Scientists say time can bend. Around massive objects like black holes, time actually slows down. The faster you move, the slower time goes for you. So, if you could zoom around the Earth at near light speed, you'd age slower than everyone else. And there's more. Every second, your brain processes time, helping you make sense of the world. From the rhythm of your heartbeat to the ticking of a clock, it's all about time. Time is both a physical phenomenon and a subjective experience. It's intertwined with our existence, shaping our reality and perception. All of these concepts of time are held as common knowledge. However, what truly is time? Our understanding of time remains widely misunderstood and vastly incomplete. Truth is, time continues defying a clear and unified description throughout the scientific community. Here, we will discuss a clear description of time that will enhance our understanding of the universe by deconstructing time into its components and behaviors. So, what is time? Is it continuous, or is it incremental? If it is continuous, then how does speed determine the rate of time? If it is incremental, what defines an increment? Imagine time as a film, seemingly continuous yet composed of changing incremental fragments. These fragments are akin to individual frames. And the frame rate is limited by the speed of light. This limitation is what is responsible for time dilation as we experience it. However, if this is indeed the case, what constitutes an individual fragment or instance of time? To better understand, imagine a flame emanating from a lighter. If I were to ignite this flame and refrain from extinguishing it, then repeatedly ask you every 5 seconds whether it's the same flame or a different one, what would your response be? The answer will vary depending on who you ask. Some may respond that the flame is different, while others will claim that it is the same one. This illustration of a burning flame not only highlights the absence of a unifying definition of time amongst our intellectual community, but also illuminates the way humans perceive its transition. What we perceive as continuity is, in reality, composed of numerous discrete instances of time. Different gas and oxygen in each instance define a slightly different flame each time I ask you the question. But what is the rate of each instance of time? Is each instance equal, or do they vary? Also, how much can we minimize this increment until we are only reflecting on our present instance of time? Here lies the conundrum. However, what if we could answer these questions? Is there a theory of time that successfully addresses these inquiries that elude us? Well, there actually is. Revered theorist and author Charles Aprile eloquently expounds upon this concept in his book Aprile's Unification with Certainty, Bridging Quantum and Classical Theory. Among other topics, he delves into the nature of time, tackling its enigmatic nature that has long evaded our understanding. It is a captivating exploration we will briefly discuss in this video. Now, consider our flame. It consists of many individual increments of time, clearly, but what if we define each instance as merely a change of parameter? Essentially, any change of parameters, no matter how minor, constitutes a new instance of time. So simple, yet so profound a notion. Then, things begin making sense. This means that each instance of time has its own set of parameters. So, a parameter change would be what signifies a progression or new instance of time. It truly is this straightforward. And these changes in parameters are constrained by the speed of information transfer, which happens at the speed of light. which then explains why time ceases to progress at light speed. Let's delve deeper into this concept for more clarity. Visualize our flame frozen in time. Let's say it is traveling at light speed. Based on our current understanding of space and time, as explained by Einstein, the flame would experience no progression of time. Now, let's explore the implications of this temporal stasis for the flame. Please keep in mind that this remains a purely theoretical exercise. As our current understanding stands, a flame could never attain light speed. The answer, surprisingly simple, lies in the unchanging parameters. Imagine a flame hurtling through space at light speed. It would retain its original state throughout the entire journey. At this velocity, no informational alterations occur. Without fresh oxygen or additional fuel to sustain combustion, the flame would appear precisely as it did upon departure, even if eons passed in our time. Each particle of the flame, forever outpacing any potential energy interaction, steadfastly maintains its original characteristics. In this scenario, the flame would effectively become suspended in a single instance of time, devoid of any energy interactions. Without particle interactions, there would be no variation in parameters. Consider what unfolds at light speed, the ultimate velocity permitted by the universe. At this extraordinary pace, nothing can overtake from behind, not even another entity traveling at light speed. Now, imagine, for a moment, light itself encountering a particle moving in the opposite direction. In that fleeting moment, as light interacts with the particle, it undergoes a change in energy levels, or in other words, experiences a change in parameters. Then, before it reflects in a new direction, it experiences a brief instance of time before hurtling forward at the speed of light. In the case of our flame, the absence of energy interactions or changes in parameters results in the flame being frozen in a single instance of time. Now, imagine that suddenly, a single photon collides with our flame, causing an interaction. This seemingly minor event slightly alters the flame's energy levels, resulting in subtle changes to its parameters. Remarkably, this very interaction constitutes a new instance of time. As each new particle interacts with the flame, whether it's a photon or another subatomic particle, it causes an exchange of energy and a new instance of time emerges. We, therefore, can finally define time. Time is the rate at which parameters change due to energy interaction. Each change of parameters constitutes a new instance of time. These changes in parameters are bound to the speed of particles. This comprehension of time opens doors to a deeper understanding of the cosmos. As we know, the phenomenon of time dilation occurs due to a variation of speed between an object and observer. Matter at rest experiences time in its entirety. Essentially, time passes more rapidly for stationary object and slows down as an object's velocity increases. However, what if this arises because the faster an object moves, the longer the intervals between particle interactions? Consider that it's not solely an object's speed that affects the time it experiences. Rather, it's the interactions that define this experience, and these interactions are influenced by the object's speed. A clear distinction that we must understand to properly and accurately define and explain time. For instance, consider two motorcycles racing down a track. In this scenario, let's assume that the motorcycle in the rear is traveling a few miles per hour faster than the one in front. If the riders maintain their current courses without altering them, an accident or interaction between both bikes will certainly take place. The precise location of this interaction on the track depends on the relative speeds of the vehicles. For particles, time is uniquely defined during interactions, and a fresh instance of time emerges with each particle interaction. Now imagine an object in the empty vacuum of space. Not space as we observe it, but rather a deep space where no other particles are around the object. In this thought experiment, would our object experience time? According to this definition of time, the conclusion would be that the object experiences no passage of time whatsoever. Without any particle interactions, the object would remain unchanged, neither decaying nor altering energy levels or any other parameters. How then could time be quantified or measured? Indeed, it cannot. The reason lies in the fact that time is not yet a reality for this object. Without any particle interactions, not only can time not be measured, but velocity and position also remain immeasurable. Does time not require both? Now, imagine directing a beam of energy to strike our object. What unfolds next? Energy interactions take place, and the object begins to transform. It is at this juncture that the concept of time emerges. Time can finally be a reality, because even though the effect may be ever so slight, there will be a measurable change in our object as it undergoes transformation. And this measurable change represents time. Let us now imagine changing the frequency and intensity of this beam of energy. Consider reducing the beam intensity significantly so that only one particle strikes the object per hour. In this scenario, the object would undergo changes over an extended period of time. This gradual transformation signifies that time passes slowly for our object. Keep in mind, it is not time itself that is technically slowing down, but rather, fewer instances of time are created due to less change of parameters. This difference is important to understand. Time is not continuous and slows down. Time, rather, is incremental and less increments of it emerge, which is perceived to us as time slowing down. Consider an analogy. If time were a rubber band, it would not be a continuous one that stretches and contracts, but rather, it would be a segmented band, each new fragment determined by energy interactions. The fewer number of segments, the slower time passes. The more segments, the more instances of time and the faster time passes. It's not the segment size that constitutes time, but rather, it is the transition between segments that signifies a new instance of time. Time progresses, or parameters change, at the point of each new fragment or energy interaction. The phenomenon of time dilation, as illuminated by Einstein's theory of relativity, arises from this profound distinction. An object is not tethered to a universal clock shared with all other entities. Rather, it exists within its own temporal domain, its passage of time uniquely calibrated by the very interactions it undergoes. This individualized measure of time, distinct for each entity, is what shapes the fabric of their reality, determined by the forces they encounter. This also elucidates why the constancy of time's rhythm, as perceived from your own vantage point, remains unchanged whether you stand still or soar at breakneck velocities. Rather than time changing its speed, it's more accurate to say that fewer or more instances of time occur based on the particles' interactions you experience, which are affected by your relative speed. Now, on the other hand, let us turn up our beam. So much so that a particle every second hits our object. Clearly, the object would change quicker because energy interaction has increased. This would represent time speeding up for the object. The rate of change in its parameters increases, and the measurable effects happen quicker. Essentially, more instances of time develop due to an increase in changing parameters. Now, let us put our object in motion. Consider an object moving at 99.9% of the speed of light. At this velocity, each particle in our beam will take longer to reach the object compared to a lower speed. While the speed of light remains an unwavering constant, traversing the vast expanse of space, even at this ultimate velocity, demands time. Therefore, particle interactions are influenced not only by beam intensity, but also by the increased time it takes for each photon in our beam to reach the object in motion. Hence, particle interactions depend not only on the beam's intensity, but also on the object's speed. If we were to slow the object down, then the more we decrease its speed, the more energy interaction that will occur depending on beam intensity and frequency. The interplay between our beam and the object in question is governed by these two fundamental principles. This occurrence is what defines time. When energy interaction takes place, time progresses to a new instance. It is important to note that the concept of time is not inherently tied to a specific direction of travel. If direction were a determining factor, we would expect time to vary depending on whether an object was moving forward or in reverse. However, our observations do not align with this expectation. The progression of time can be defined only as a change in parameters. This means that any alteration of parameters signifies the passage of time. However, what are the implications to this? Well, consequently, it would mean that traveling back in time would be impossible. Even if we were to recreate all the previous parameters from a past moment, doing so would still constitute a change in parameters, ultimately advancing time. It implies that any attempt to recalibrate parameters to align with a past moment in time would, paradoxically, propel time onward. Each adjustment, intended to echo the past, becomes a new parameter change, advancing the very continuum we seek to revisit. This inherent progression of time is an inescapable truth, a testament to time's unyielding march forward. In his publication, Charles Aprile offers a profound exploration of this concept for the intellectually curious. He introduces a thought experiment as a means to explain his assertion, inviting readers to engage with the idea through a vivid mental simulation for those who are interested in learning more about this concept, or for those who enjoy engaging in self-debate. However, this viewpoint not only resonates with logic, but also adeptly captures the essence of time as we perceive it. It's a perspective that aligns with empirical evidence, offering a coherent narrative that mirrors our lived experience of time's passage. So, what does time mean in the subatomic universe? Specifically, let's explore the behavior of light as it travels through space to gain some insight into this idea. Light, being composed of photons, plays a crucial role in our understanding of time. As photons zip along, time behaves differently for them compared to our everyday experience. Due to their incredible speed, photons effectively experience timelessness. From their perspective, their journey is instantaneous as they traverse vast cosmic distances without any sense of duration. For instance, when light departs from a star, an intriguing phenomenon occurs. Time appears to freeze from the perspective of the photon. Imagine a photon traveling a staggering 100,000 light-years before reaching Earth. Remarkably, the photon experiences this entire journey as if it were instantaneous, hitting our planet at the very moment it departed from the star. This phenomenon, accepted within the field of physics, underscores the mind-bending nature of time and the relativistic effects experienced by light. But what happens as it journeys through space without making contact with anything else? Well, as we have discussed, if it doesn't interact with anything, then clearly no energy interactions take place and, consequently, no new instance of time occurs. Hence, the photon experiences no time. This principle applies universally to photons and all elementary particles alike. It is the interplay of velocity and interaction that shapes our understanding of relativity, where each object navigates through the cosmos on its own temporal trajectory. The speed at which an object moves directly impacts its interaction, granting it a unique realization of time that is relative due to its own state of motion. By defining time as an incremental consequence of particle interactions, we unlock boundless possibilities for advancing our understanding of physics. This elegantly simple concept, proposed by Charles Aprile, reveals pathways to profound insights and yields a cohesive, unified definition of time. It is with a more detailed understanding of time that may finally allow us to bridge the gap between classical and quantum theory. Through this lens of time, we might reconcile the macroscopic predictability of classical physics with the probabilistic nature of quantum mechanics. Thank you for embarking on this intriguing journey through the multifaceted landscape of time. Your curiosity and engagement have illuminated our exploration of this captivating subject. Until next time.